Good morning, everyone. I'm Brock. So today, let's keep working on a LeetCode quiz question. So this question is matchsticks to square. You are given an integer array. Matchsticks, well, matchsticks I is the length of the i's matchsticks. You want to use all the matchsticks to make one square. You should not break any stick, but you can link them up. And each matchstick must be used exactly one time. Return true if you can make this square and false otherwise. Okay, I think this question is pretty, this requirement is pretty straightforward. Similarly, let's use a test case to find a specific solution, then generalize it. Okay, so let's get a input. Let's say 5, 5, 5, right? 4, 4, 4, 3, 3, 3. So you see? Okay. So what's the first step? We need to know the total target, right? And then we will know, from the total length, we can know, how long each. Oh, how do you say that? Side length.
Side length.
Side length.
Side length.
Side length. Yeah. So from the total length, we can know what should be the side length, right? And then we can try to sort the sticks descending, right? So sticks descending. And in our case, so sticks, let's say, sorted. In our case, it's very straightforward because it's already, sorted, right? And then what we need to do? Then we need to use maybe DFS. So start DFS is mask is equal to 0, which means no sticks used. And the size down is 0, which means no full size. And the current sum is 0, which means, right, current set length sum. So we need to put the first stick. So pick first stick. So in this case, this stick will be what? Index 0, right? And how long it is? The length will be 5. And so when we pick up the first stick, the mask will need to update accordingly, right? So it will be 1 left shift 0. Make sense? Right? It's our original mask is 0, 0, 0. And then we make the number, the last integer, left shift 1 bit. So the mask will be 1. New mask. And current sum is 5. Make sense? And then what we need to do? We need to pick next stick, right? And that next stick index will be 1. And length again is 5. So the new mask will be so basically the second one is to make the second bit become 1. It's actually, you will find it's actually 2 power 2 minus 1. Right? So new mask will become 3. And the current sum is previous the sum plus the, the new element is 10. And then we need to our target divided by 4 will be 12. Then what do we need to do? Now we already get 10, and we have 2 more from the stack. Now we try to add, now 5 doesn't work, 4 doesn't work, 3 doesn't work. And it's too long, so it will get rejected, right? Try to add 4 or 3. Length, matchstick. Right? But then the current sum will larger than 12, then rejected. Make sense? If that happened, what we need to do? We need to try different compilation, right? So we need to try different compilation until what? Until current sum is equal to 12, right? That's what we need to do. For the second, third set, then it's done, right? Continue to fill second and third side, right? If the set down is 3, then return true. Make sense? So the basic idea is to use DFS to find the side that can to meet the requirement, to calculate together and get the target. Okay. So our input is matchsticks, which is a list int. And our return type is bool. Okay. So first thing, let's initialize total. And then what do we need to do? We need to get the value, right? So we need to accumulate sum of all matchsticks. So which is for value in matchsticks. What we need to do? We need to add them into the total length, which is total length. Make sense? Then what do we need to do? We need to ensure it can be divided by 4, right? So we need to check if total length, if not divided by 4, then we just write down total length mod 4 is not equal to 0. What do we need to do, right? We need to return false. Make sense? After we get the total length, we just use total length divided by 4. Right? And here we need integer division. And then we need to sort the matchsticks. So the sticks sorted matchsticks. And we want to get a descending sequence. So we make reverse as true. Okay? But also we try to think about some edge cases as well. So if the longest stick is longer than target, again, we're done. If the stick right, if it is empty, then we return false. If the longest is larger than target, we are also done. Make sense? Now what do we need to do? We need to know how many sticks we have, right? How many sticks we have. And here we can use a building function, the cache. Memorize DFS on parameters, right? Then let's define a DFS. So help function, right? Def DFS. What input we have? We have mask, right? And we have site down. We have current sum. That's what we have. As mask is the integer bit mask. And set down is how many sticks have been fully formed. The current sum is current accumulated length on the set being formed. Right? So again, let's think about some, edge cases. If we already, right, completed 3 sites, then we are good. We find our targets. So if side down is 3, then we just return true. Right? And if the current site reaches target, then we can start to build next site. Right? If current site reaches target, then we start building next site. Right? So if current sum is target, so we return DFS mask next set current sum is 0. Make sense? Okay. So we initialize the index first. So then what we need to do? We need to iterate over indexes from 0 to n-1, right? Because the whole length, because we get n matchsticks, so we need to iterate of them. Well, n smaller than I smaller than n, what do we need to do? We need to check if the stick is unused in the mask, right? So we need to check if stick I is unused in the mask. So how do you check that? We will use the bit is the mask. Right, redshifts. Then add 1. Redshifts. Right. This is to right shifts the bit in mask in I bit. And then what we need to do? We need to check if this stick unused, right? So if a user bit is 0, which means it's unused, then what do we need to do? We need to add it into the length, right? Okay. Get the length. And then we need to check whether exceed the target, which means that we will check if current sum plus stick smaller than target, correct? If smaller, then what should we do? So we should side bit to mask stick used, right? So I1 left shift I. Make sense? And then we need to recurse with updated mask and the new current sum. So if DFS new mask and the size current sum minus stick length. If we find it is true, then we return true. Right? If the recursion succeed, then we can propagate true. Make sense? And then if current sum is 0, then which means if current sum is 0, what should we do? Just return false, right? And if adding the stick exactly filled the side, right? Right? If adding this stick fills the side, but leaves future failing. So if current sum plus stick length is equal to target, then what do we need to do? We need to return false. Right? Let's also get an index. And we need to skip sticks of the same length, correct? So j is smaller than I, and the sticks j equals to sticks I. Right. If that's the case, aj just increment by 1. Then j set I to the next non-duplicate index, right? Again, I still think that Python's indentation sometimes is very confusing. It's hard to find, which is a mapping for the loop, right? Because I may if a stick is already used, again, let's move to the next one. Right, if we cannot find, we return false. And what we return, true or false, is a DFS, right? The mask is 0. The size we completed is 0. The current sum is 0, right? Let's run it. I think that there should be some maybe syntax error. Yeah, I know. If size down is equal to 3. Okay. Return. Okay, the cache not designed. Guess this requires some import, right? So assume function tools import, right? Import caching decorator. No function named function tool. Oh. Cannot import. Cannot import. Interesting. Interesting. Yeah, and not import. Okay, then we just ignore. Okay, stack. Stack. I think it's stacks, right? Yeah. Okay. Let's try it. Okay. So the time complexity is okay. Yeah, somehow it cannot show the time complexity and the space complexity. But anyway, I think this one, because we utilize, the bit operation again, let's let GPT to explain. So explain the building functions, methods, operators, and the step-by-step test case, inverse the case for the code. Right? So because here, now when we rethink the whole thing, the key is to use depth-first search to find values that added that the summary the sum is equal to the site. That's the key of the logic. Okay. Yeah, here are some operations we have done. Yeah, so for value in matchsticks, this is for loop. Iterate each element of list. Plus equal operator, add two values in place. Mod operator, modulars, give remainder, divided by operator, floor division. For example, 13 divided by 4 will be 3. Sorted. Matchsticks reverse is true, is built-in function. Sorts list descendingly because reverse is true. Len sticks, built-in functions, return numbers of elements. Larger operator, greater than comparison. Bitwise right shift. Mask bitwise right shift moves bits right I times. Used to check if stick I used. right? Imagine if stick I is used, then when you right move I times, then the last bit will be 1. And bitwise AND. So when we right shift, so we move the bits right I times in mask and 1. Then we isolate the I bit equals 2. Equally comparison. Compare if two values equal. Return keywords exit function with a value. While I smaller than n loop iterates until condition false. If else, conditionally control flow. LRU cache decorator. How to translate decorator? This will memorize DFS calls by caching. Okay. Also, let's understand more about decorate. What's decorator in Python? So a decorator in Python is essentially a function that modifies another function or class without changing source code direction. It's a way to wrap exact actual behavior around existing code. A bit like giving a function superpowers by putting a transparent wrapper on top of it. Suppose you have a function print out hello. Now you want every function in your program to automatically log when it starts and ends. Instead of rewrite all your function, you can decorate them. So what it does is okay. We define a logger function. And you define a wrapper when you call this function. Okay, you will get to come out. So the log line means so logger takes grid as input and return a new function wrapper and add edit before start and after call. Okay. So what under the hood? Python raise your function definition top to bottom. So when it reach when it reach the grid function, it equivalent to make grid is log grid. The decorate logger returns a new function that wraps grid. From now, calling grid actually call wrap. Okay. And here I had an example for LRU cache. Okay. So this will tell Python cache every result of DFS. based on its arguments. If I call DFS 518 again, just reuse the old results instead of recomputing. That turns explosionary recursion into a must fast memorize search. You trade memory for time. Okay. So decorate is like wrapping a gift. A gift, your original function, the wrapper, decorate that adds a message, tag, or extra flair. When you hand it to someone, try open the wrapped version, but the inside content is still your function. And then let me ask him, what does LRU cache mean? I think it's, yeah, least recently used cache. In interviews, sometimes we will ask to design a cache system. Most of the time, it's least recently used cache. Yeah. Cache size is unlimited. When cache is full, the least recently used entry is dropped. That's the basic idea. Okay, let's go back to our original thing. Okay, so yeah, just now we explained the building function and the methods and operators we use in this algorithm. And then now let's use let's visualize. So here we have a test case, right? The total length will be 48 and target is 12. After sorting, we get the sticks list as 555, 4444, 3333. Okay? So at the very beginning, the mask will be 0, which means that we get a binary of 12 zeros because no sticks used yet, right? Size down is 0 because we start from first side. Current sum is 0 because no length yet. So the first step, we need to build set 1, right? So we try stick 0, which the length is 5, and the new mask will be 1. Makes sense? And then the current is 5. Then we try Lexa stack, which is now the mask becomes 3. And then the current sum is 10. And then we try the second stack. Now the current sum becomes 15. Larger than 12, we reject. So we cannot use another 5. Then basically we try everything else. So which means we cannot use another 5, then we backtrack. And backtrack to find a 12 combination. So again, we choose, for the first mask, we choose 0. And for the second stick, we choose 4. And the new mask will be 17. And the current sum is 9. And then we choose the third stick. And the third stick, and then we get the new mask as 273. The current sum is 12. It's good. So now we find the first side, and we move to the second side. Okay. Now the value sides down is 1, because one set is down, right? And current sum is 0, because we start a new set, and current mask is 273, which means that stick 0, 4, 8 are used. Okay. So post-book compilation will be 5, 4, 3 again, but skips use the stick. So DFS will try permutations exhaustively. What does this mean?
Permutations.
What does this mean? Okay, exhaustively, 穷举 exhaustively. Okay, so stick 1 is 5, stick 5 is 4, stick 9 is 3, then valid. So now size down is 2, and mask masks 6 bits as 1, because we already used 6 sticks, right? Then we build set 3 similarity. After computing these 3 slides, base case, right? If size down is 3, then we trigger and return true. Make sense? Yeah, here's some clarification. Each stick can either used or not used in each recursive pass. So the theoretical versus the case DFS complexity is O 2 to the power of n. Here, n is 12, which means we need to do at most 2 to the power of 12, 4,096 recursive states. Each stage iterates n, which is 12 sticks. It's around 49,000 operations, manageable. But if we enable the least recently used cache, then memorization will cache all visited compilations. It will provide massive speed up. Yeah, and here are some, bitwise operations. So I left shift 1, left shift I means move 1, left shift move 1, left shift I bits. So for example, if I is 3, then we move 1 from the last bit to from the 0th position to the the 3rd position, right? Size bit I. And the mask right, left I, and 1 means. So first thing, we will this is our mask, right? We will right move 3 items. So which means that the third item will be moved to the zeros position, and we find is 1. It's good. So this is used to check if sticks are used. So if you think about it, when we use left shift, most of the time we do left shift to cite a bit. But when we use right shift, right shift to check if a bit is used. Make sense? Yeah. So some key tricks we use here. Mask is to track subsite state. And backtracking prunes impossible path early. Descending sort ensures bigger sticks fill earlier, reducing branch count. Memorization avoids recomputing states, the same DFS value. Okay, yeah, I think that that's pretty much for today's question. And I noticed that we use a lot of bit operation and either DFS or DFS strategy. Okay, thank you everyone. Bye.